5-minute quiz. A microscope that can see inside the tissue is something, something, something microscope. This video is presented by Center for Molecular Spectroscopy and Dynamics, IBS, at Korea University. We have been in a car at some point looking outside through the window. The water vapor in the fog makes objects blurry or invisible, and objects seen through water droplets on the window look distorted. As light passes through the turbine medium, the wavefront of light is distorted due to the spatial variation of the reflex index of the medium. These wavefront distortions are largely classified into aberration and scattering. The wavefront distortion on a spatial scale much larger than the wavelength is called aberration, which causes the image to be blurred or distorted. Scattering of light is mainly due to the refractive index variations on a scale comparable to the wavelengths of light. Multiply scattered light causes considerable speckle noise in the image. Therefore, if aberration and scattering can be reduced, clear images can be recovered. Imaging living tissue, such as human skin, with an optical microscope is similar. The skin tissue is highly turbid and is densely composed of various substances. The deeper the light propagates into the skin tissue, the more severe the aberration and scattering becomes. Up to date, conventional optical microscope for in vivo skin imaging with visible light is limited depths of just few hundred micrometers. Non-invasive imaging of living mouse brain through the intact skull is an ideal, but challenging application in neuroscience research. A heterogeneous skull bone structure induces complex aberrations and severe multiple light scattering, and thus, without opening the skull, you can see it in the fine structures of neural systems like the image in the middle. Thus, the existing imaging technique necessary that the skull to be either removed or thinned to microscopically analyze the neural networks of brain underneath. We introduced a new type of microscope called refractive matrix microscope that can see through a highly turbid sample. First, multiple holographic images of electromagnetic waves reflected from the sample are taken by camera, and distorted wavefront distortion is removed by displacing a compensation phase pattern on a spectral light modulator (SLM). After the compensation, a clear image without aberration can be obtained with a photo multiplier tube (PMT). This shows the holographic image of the refractive waves measured by scanning a focused laser beam across the target inside the turbine media sample. As you can see, the refractive wave fields are spread by sample-induced aberration and scattering. The measured holographic image of reflective waves are transformed into a reflection matrix. A novel aberration correction algorithm called CLASS is then applied on the reflection matrix to computationally find aberrations and aberration-free target images. The CLASS algorithm iteratively defines the aberration in illumination and detection paths and the target image separately. As the iteration continues, the target image with aberration correction becomes sharper. After a few iterations, it converges into a final optimal image with a significantly improved image quality compared to the image without aberration correction. For aberration-free, multi-photon fluorescence imaging, the excitation laser beam must be tightly focused onto the target location, which requires physically correcting the wavefront distortion undergoes by the laser beam. For this reason, computationally found wavefront correction map is displayed on the SLM. This result shows the performance of wavefront correction by SLM. The image on the right, in which the sample-induced wavefront distortion has been physically corrected with the SLM, looks much clearer than the image on the left without aberration correction. It can be also seen that the point spread function after wave correction is much sharper than the without correction. This hardware wavefront correction technique was applied into the 2-photon fluorescence imaging of neurodendrites beneath the mouse skull. When the wavefront was not corrected, no myelin fiber was seen through the reflective image, and the dendrites are not clearly visible in the fluorescence image. However, After the wavefront correction by the SLM, myelin fibers were clearly visible in the refractive image and the fluorescence image. Thin spine necks as well as dendritic spines were captured with a spatial resolution as close as the diffraction limit. 5-minute quiz. A microscope that can see under the tissue is something microscope. The answer is reflection matrix microscope. Lastly, if you found this video interesting and useful, please like and subscribe. Thank you for watching this video. This video is presented by Center for Molecular Spectroscopy and Dynamics, IBS, at Korea University.